In this video, we're going to talk about electrolysis. You can read about this in Chapter 17, Section 7. And in particular here, we're going to talk about the differences between a galvanic cell and an electrolytic cell. So a galvanic cell or a voltaic cell, those are the cells we've been talking about so far. And in those cells, energy is released by a spontaneous redox reaction. So we're converting the chemical energy of the redox reaction into electrical energy. We said before that oxidation occurs at the anode, which is the negative electrode, where we're removing electrons from the anode and we're sending them, they're migrating toward the cathode, where reduction occurs. So in an electrolytic cell, now we are adding electrical energy in order to drive a non-spontaneous chemical redox reaction. So another way of putting that is that instead of converting chemical energy to electrical energy, we're converting electrical energy into chemical energy. We are storing that electrical energy in the bonds of the products. So we're making higher energy products than our reactants. Oxidation here still occurs at the anode, and reduction still occurs at the cathode. However, we notice that the anode is now the positive electrode and the cathode is the negative electrode. Okay, so reviewing that, oxidation still takes place at the anode and reduction still takes place at the cathode. However, the cathode is negative because now the electrons from the voltage source, which is either an electrical outlet, the grid, or a battery, the electrons from that source are migrating toward the cathode in order to help with reduction. And likewise, the anode is positive now because electrons are being removed from it. So this is an opposite convention compared to the galvanic cells. Now, the prototypical electrolysis cell that we always use to teach students is the electrolysis of molten sodium chloride. So, in molten sodium chloride, we have taken salt and we've heated it up so that it's now a liquid. And there's those ions present, and we can add electricity in order to produce chlorine, so to convert chloride into chlorine, and to convert the sodium ions into sodium metal. So, in the electrolysis of molten sodium chloride, which of those reactions occurs at the anode? Well, here we don't have any water, we just have sodium and chloride, so neither of these water reactions are relevant. And instead, we can think about either sodium ion becoming sodium metal, so there the sodium is gaining electrons. Reduction is gain of electrons, so this is reduction. Or we can think about the chloride ions losing electrons as they become chlorine, so this is oxidation. All right, and so since we're interested in the reaction that occurs at the anode, that's going to be the oxidation reaction. The other reaction is going to occur at the cathode. So that means that the chlorine electrode is the anode and the sodium electrode is the cathode. Okay, in an electrolysis cell, we can also calculate the potential of the cell using standard reduction potentials the same way that we've done before. However, we're going to expect a negative cell potential instead of a positive one. So let's consider a water electrolysis cell. So in this cell, we start with water. And we can oxidize it to form oxygen gas and protons and electrons. And the cell potential, the standard cell potential for this reaction in the direction that it's written is negative 1.23 volts. So here it's written as an oxidation, so I've flipped the sign. If you look this one up in your table, you'll see that it's written in the opposite direction as the reduction of oxygen to form water, and the cell potential will be positive. Okay, and then the other, so that's one reaction. The other half reaction is protons from water get reduced to form hydrogen gas. So in our water electrolysis cell, we produce oxygen and hydrogen. We produce oxygen at one electrode and hydrogen at the other. Now, this reduction of protons to form hydrogen is the standard hydrogen electrode. So its cell potential is 0 volts. And so that means that if we add these together, we get that the overall potential for our cell is negative 1.23 volts. So our negative cell potential tells us that this is a non-spontaneous reaction. So we have a voltage source to supply that extra energy. And we see that the anode is the positive reaction where the oxidation of water to oxygen occurs, and that the cathode is the negative electrode where the reduction of protons occurs. Okay, so now let's consider an in-between case. We have the electrolysis of aqueous sodium chloride. Okay, so which of these reactions occurs at the negative electrode? So the negative electrode in an electrolysis cell is the cathode. So we're going to imagine that a reduction reaction happens. So first, the only ones that really matter are the reduction reactions. Okay, so if we sort of simplify, like the A and B are both reductions, C and D are oxidation. So let's focus on A and B. Now, which of these has a more positive potential? Which one requires less input of energy in order to make it happen? The one with the less negative potential is the water reaction. So in the electrolysis of aqueous sodium chloride, at the cathode, we're going to have the electrolysis of water, or the reduction of water to form protons. To form hydrogen. And we're going to do that because it has the smaller negative reduction standard potential. Okay, so same analysis. Which of these reactions occurs at the anode? So the anode is where oxidation happens. So let's focus on the oxidation reactions in our list. We could either oxidize chloride to chlorine, because we have sodium chloride, or we could oxidize water to oxygen and protons and electrons. So let's think about which of these requires less input of energy in order to happen. So if you look at our options here, we see that the water reaction has a smaller negative voltage, so requires less energy to input. However, fun fact, that is not actually what happens. What actually happens is that the chloride gets oxidized to form chlorine gas. So if you put an anode and a cathode and hook it up to a battery in aqueous sodium chloride, you will get hydrogen at the cathode and you'll get chlorine at the anode. Whoa, where does that come from? We predicted using the potentials that 1.23 volts is smaller than 1.36 volts. What explains this difference is something called overpotential. So in general, the reaction with the lowest potential, in this case the least negative potential, happens. However, sometimes our predictions are incorrect, our thermodynamic predictions, because of something called overpotential. So overpotential is the extra voltage required for an electrolytic reaction to proceed at an appreciable rate. This is kind of like or related to the activation energy. So in addition to the thermodynamic energy, the standard potential required, we also need some extra potential in order to add the required activation energy for the reaction to occur. And so that the water electrolysis or oxidation reaction that we talked about before has a higher overpotential than the chloride oxidation process. So the chloride process ends up being faster. Now, the size of overpotential cannot be predicted. So that means that I can't expect you to tell me which of those is going to happen when they're close, given that we can't know how big the overpotential is without measuring it. So, in general, you can make a prediction that the reaction with the lowest potential should happen. However, it's possible to be surprised because overpotential is a factor.